All right, Module 19 is going to wrap up a part of the course for us where we've been studying reactions of alkenes. I'm going to add in this section on this last module is going to be on reactions of alkynes, which are analogous to reactions of alkenes that we've seen. So there's not a ton new here, but there are some twists because alkynes start an oxidation level higher than alkenes. In some cases, we're going to see different results than what we got with alkenes. Um, so let's start. Um, we know that for an alkene, we saw that the HOMO was pi cc and the LUMO was pi star cc. And that generally what we found was pi cc, this orbital that looks kind of like a hamburger bun, is a decent donor. And that's what happens in most reactions. We see that act as a donor. Occasionally, we saw pi star CC act as an acceptor, but that was rarer. Well, think about an alkyne. In an alkyne, the HOMO would again be pi CC. The LUMO would again be pi star CC. So based on that, it should not be surprising that these two are going to do very similar reactions. Um, and that's what we're going to see. So I'm going to start with the reaction with a strong acid HBr, which we saw with alkenes. We're going to see a similar reaction with alkynes. Take a minute and see if you can draw yourself a mechanism for this reaction, and pause the video, draw your mechanism, and then come on back to take a look at it together. Okay, so I have my alkyne, and I can see I'm adding HBr. I'm told that it's in excess. That means more than one molecule of HBr for each molecule of the starting material. So I'm going to have to use HBr more than once in my mechanism. But it won't surprise you, hopefully, to see that our first step is for pi cc to attack sigma star HBr. That's going to leave us a carbocation. So here's my carbocation intermediate. I have a choice. It's an arbitrary choice, but I've got to choose whether to put the carbocation on 3 or 4. In this case, since on my product, my bromine is on carbon 3, I'm going to put the carbocation on 3. That means I added this hydrogen here to carbon 4. It could be implied, but I'm going to draw it in just to be explicit. So I make this carbocation. Now, one thing to note about this carbocation is the carbon number 3 here has a double bond and a carbocation. When a functional group or a substituent is on an alkene carbon, on the double bonded carbon, in many cases we'll label that as a vinyl group. So this would be known as a vinyl cation, meaning the double bond is on, the carbocation is on the carbon of an alkene. These carbocations are slower to form than your regular carbocations. Part of that has to do with the hybridization. The hybridization would now be sp. That makes that carbon effectively a little more electronegative. So that carbon is going to be more reluctant to take on the positive charge. the bottom line is we won't see these carbocations on alkenes as often. They are a little slower to form. I'll show you a case where that's relevant in the future. But in this case, where we're reacting with the very strong acid HBr, we are able to form this vinyl cation. And now my second step is going to be to note that a carbocation falls in love with the first nucleophile it sees, which in this case is going to be the bromide ion. And that's going to give me this intermediate here. All right, I can see that I'm not at my product yet. I still have an alkene in the molecule, and I still have more HBr around. So I'm going to repeat that step where pi CC attacks sigma star HBr. And now I have a choice, and it's not an arbitrary choice. I have two options. I could leave the carbocation on carbon 3 or on carbon 4. So in other words, this new hydrogen that I'm adding, I could add the hydrogen to carbon 3, and that would leave a carbocation at carbon 4. Or I could add the hydrogen to carbon 4, and that would leave a carbocation at carbon 3. All right. Unlike the first case where 3 and 4 were indistinguishable, now there's a difference. So the question becomes, do I want my carbocation on the carbon with bromine or on the carbon without bromine? And the answer is that bromine has a lone pair. So remember, if I have this carbocation, I can have an alternate resonance structure where bromine is donating electron density. I'm going to leave out the implied hydrogens. I'll include them here, but I'll leave out the implied hydrogens in this next structure. I have an alternate resonance structure where bromine is stabilizing the positive charge. So this is a resonance stabilized carbocation. Whereas here there is no stabilization. All right. So based on that, I would say we are unlikely to form this carbocation. It would be formed much more slowly than the carbocation where the bromine can resonance stabilize it. So that's why whenever we do this reaction, we will add both halides to the same carbon atom, rather than one to one carbon atom and one to the other. So my last step would be to have my bromide ion go ahead and attack the carbocation, and that gives me this observed product. So I've introduced before the term vicinal. I'm going to introduce another term now, geminal. You may know Gemini as a zodiac sign, meaning twins. So geminal is like when you have twins, two groups bonded to the same carbon, not to neighboring carbons. So vicinal meant bonded to neighboring carbons, so they're in the same vicinity. Geminal means they are twinning, they're on the same carbon. So this would be a geminal dihalide. We've seen before that we could make a vicinal dihalide by reacting an alkene with Br2. This would be a way to make a geminal dihalide. I point out these language things because when you take a future organic chemistry class, they might not always point out these subtleties to you, and they'll just dive into using the terminology. So I want you to have some background in where these terms come from. So there's a reaction that produces a geminal dihalide. And the theme that I want you to take away from this reaction is alkynes do a lot of similar reactions to alkenes. And so when you're framing these things in your mind, keep that in mind. The next slide expands on that theme, where we're taking reaction of an alkyne, and in this case, reacting with a halogen rather than an acid like HBr. Now we're reacting with Br2. Well, just to point out this first case, one equivalent means 1-to-1 ratio of alkyne to Br2. So for every 1 molecule of, or 1 mole of my alkyne, I'm adding 1 mole of Br2. That's what that terminology, one equivalent, means. So we've seen this reaction before with alkenes. With alkynes, it's going to be a very similar mechanism where pi CC attacks sigma star BR. At the same time, we have bromine lone pair attacking. That's going to form as an intermediate our bromonium ion, but in this case, it's still got a double bond, making it even more reactive. And then that is going to get attacked to give me the vicinal dihalide as predicted. So this will give a vicinal dihalide with an alkene in the middle. So you can add 1 equivalent of Br2. You could also add 2 equivalents, meaning do it again. So doing it again would be the same as just adding more Br2 to the product of the first one. And what that's going to do is add another bromine to each of those carbons. So in other words, the alkyne just does what the alkene does, but it can do it twice. These aren't synthetically all that useful reactions, so I don't want you to spend a whole lot of brain space on these. Just know that alkynes do a lot of similar things to alkenes. What if I were to react my alkyne first with HI? Well, that's going to add H to the less substituted carbon. It's going to add I to the more substituted carbon, give me this intermediate. If I then add Br2 to that, it will add a bromine to each carbon of the double bond. So alkynes will do similar things to what we've seen alkenes do. Don't want to dwell on that point any more than just to give you a few examples like this. What's another reaction we did with alkenes? Well, we did catalytic hydrogenation. We can do the same thing with an alkyne. Remember H2 and palladium on carbon. That palladium is a good catalyst, and that speeds up the reaction, allowing us to add 2 hydrogens. So I can, if I do this reaction with an alkyne, well, first the hydrogen will react with the alkyne. Remember, this is a syn addition, so I'm going to add my 2 hydrogens to the same side. That would give a cis alkene. But the difference here is I know an alkene will still react further with H2 and palladium on carbon. So this is not stoppable. We can't stop here because I know that the alkene will react with the same reagents to add 2 more hydrogens. So if I had those 2 green hydrogens, now I'm going to add 2 more hydrogens and just make the alkane. So you can hydrogenate an alkyne and turn it into an alkane just using palladium and palladium on carbon with hydrogen gas. So that would go alkyne straight to alkane. But chemists are clever, and we said, well, we would like to be able to stop. So what if we could come up with a catalyst that is reactive enough to react with the alkyne, but won't react with an alkene? And after tinkering out with different formulas, a number of different poisoned catalysts have been developed. So poisoned catalyst just meaning it's a little less reactive than just pure palladium on carbon. And one is like always, we end up naming these things after the people who discover them. So one is called the Lindlar catalyst. And the Lindlar catalyst will allow you to just add your 2 hydrogens in a syn addition and stop at the alkene. And so if you would like to turn an alkyne into a cisalkene, Lindlar catalyst is a way to do it. So hydrogenation is something we did with alkenes. We can also do it with alkynes. And we have a twist. We could reduce the alkyne all the way to the alkane, or we could stop in the middle. But chemists, get to thinking, well, what if I want something that's not a syn addition? What if I would like to have a way to hydrogenate an alkyne and make a transalkene instead? And so it turns out we've developed one of those too. This one is a bit more complicated. And the way to do it is to take your alkyne and put it in a mixture of sodium dissolved in liquid ammonia. Now, ammonia is a gas at room temperature, so you need to condense it to a liquid at a very low temperature. And then you can dissolve sodium metal in it. When you dissolve sodium metal in it, essentially the sodium metal becomes sodium plus and free electrons. So these free electrons are able to just dissolve into that solution of ammonia. You can't do this in a water solution, but it turns out at this low temperature, you can do it in an ammonia solution. And those free electrons, we've discovered, will react with an alkyne. I'm going to show you the way this mechanism is generally drawn. I'll talk about why it leads to a transalkene, and you do not need to remember these. I mean, I say here in the note that you can remember them, but you're not required. I'm just pointing them out in case you're interested. This involves a radical reaction because we have these freely dissolved electrons. Freely dissolved electrons are 1 electron at a time. So essentially, there are going to be 2 kinds of steps here. I'm going to take my dissolved electron, which I'll just write as a dot, and that is going to plop itself down on one of the carbons. That's going to break the carbon-carbon bond and create a radical on the other carbon. So now one carbon has an anion. The other carbon from the triple bond has a radical. Just to keep track, I'm going to number. Okay, so I've created a radical and I've created an anion. Well, that anion is going to be particularly basic now, and it is going to go and grab itself a hydrogen from our solvent, which in this case is ammonia. So that is a regular 2-electron step. That gives me this intermediate where I now have a hydrogen here. And I have the radical. Now, the radical, because it has that lone electron, the geometry of that isn't fixed. The free electron and the ethyl group that's coming off of carbon 4 can arrange themselves however they want. So they'll arrange themselves into the lowest possible energy conformation, which would be to put carbon 5 across from where carbon 2 is, because those two don't want to be near each other. They'd rather be far apart, just so they're more comfortable, like we talked about in Module 7 with conformations of alkanes, where groups like to be a little farther apart, so they're not bumping into each other. So this will arrange itself in a trans configuration. We'll then add a second electron from our solution. So our second electron will add itself in. That will make another carbanion, and a carbanion is a strong base, so that will go ahead and grab hydrogen from ammonia. And so in the end, our product is the transalkene. Notice that a byproduct here is we produced 2 molecules of NH2 minus, or 2 NH2 minus ions. We produced one in this step, and we produced one in this step. Oh, not in this step, in the last step. Remember that for a terminal alkyne would be one at the end of the chain. There is a hydrogen at the end. And that hydrogen turns out to have a pK of about 25, 24 or 25. NH2 minus can grab that proton to make NH3, which has a pKa of about 35. So this reaction is very favorable. So because NH2 minus is produced, if my starting material is an internal alkyne, a terminal alkyne, then I'll get this undesirable side reaction. So this is not a desired reaction. So the bottom line is we can't use this reduction on a terminal alkyne. So we can reduce alkenes to produce, we can reduce alkynes to produce cisalkenes. We can reduce alkynes to make transalkenes. If we want to reduce a terminal alkyne to an alkene, we would use this H2 and Lindlar catalyst. So this would work as well with a terminal alkyne. That works with both terminal and internal alkynes. This second one only works with internal alkynes. All right. So that's the first set of reactions I wanted to point out. I will say there is a key reaction of alkynes that I just showed here. That's an acid-base reaction. This reaction of alkynes I'm not going to cover in this module explicitly, but we will be seeing this species here again in module 20. So just be aware that's a reaction of alkynes that we're gonna talk more about, but not in this module. I'm gonna close this portion out, and then in the next portion I'll talk about a couple other reactions of alkynes that are similar to what we've seen from alkenes, but give us maybe an unexpected result.